All right, Calculus 1, aka differential calculus. This adjective differential refers to something called the derivative, which is what we're going to be studying in this class. And that's already kind of interesting that I can talk about what we're going to study in this class on the first day in a single sentence. I mean, if you compare that to like your typical pre-calculus class where we study functions, I mean, typically in pre-calculus 1, you talk about, I don't know, maybe 20 different topics. Think about like function composition, inverse functions, polynomials, rational functions, domain and range, input and output. I go on and on and on about all the different things you talk about in your typical pre-calculus 1 class. And the same thing's true in pre-calculus 2 when you get into trig functions. Unit circle, SOHCAHTOA, right triangle trig, trig expressions, trig equations, trig identities, etc., etc. Up until this point in your mathematical journey, pretty much every math class you've taken has covered a huge swath of topics. That's not true in Calculus 1. What's kind of wild about Calculus 1 is the entire class is devoted to a single topic, this thing called the derivative. And an awesome thing about the derivative is, on the very first day of a Calculus 1 class, I can explain to you what a derivative is. And that's basically going to be the goal for this section. I'm going to give you an overview of this entire class. I mean, to be fair, there's going to be lots of little details that we don't know enough to talk about right now. But at the very end of the term, if you go back and rewatch this video, which I don't recommend you do, you'd probably be a little bit surprised, be like, oh yeah, I guess we kind of did talk about the main thing that we studied for this entire term on the first day. So without further ado, pre-calculus, as I mentioned, was generally the study of functions. And probably the most basic thing you can do with functions is talk about inputs and outputs. And I'm not really going to review that here. There's a little bit of review on the homework, just to try to make sure that nobody was placed grossly inaccurately into this class. But I don't really want to waste your time trying to teach you anything that you probably already know. So suppose I give you this function, f of x equals 3/4 x minus 1. I could ask you a question like evaluate f of 4. And hopefully you're able to look at this and understand that this is kind of a mathematical machine, and this is asking me to put the number 4 in place of x into this machine. The easiest way to evaluate f of 4 algebraically is to copy exactly what you see here. Think about it as like a blueprint or something, except change all the x's into 4's, because I don't want f of x, I want f of 4. So I'm going to copy this statement, changing everywhere I see an x into the number 4. It would say f of 4 equals 3/4 times, and then instead of writing the letter x, I'm again going to write the number 4 minus 1. To evaluate f of 4, all I have to do is figure out what is 3/4 of 4 minus 1. Well, let's see, 3/4 of 4 is just 3, and 3 minus 1 is 2. So when I'm asked to evaluate f of 4, my answer is 2. In other words, if I put the number 4 into this function, this machine f of x, the number 2 comes out. I can come to that exact same conclusion geometrically instead of algebraically if I'm lucky enough to have a graph of this function, and sure enough I do. The graph of f of x equals 3/4 x minus 1 is pictured right here. Maybe you'd be able to come up with this graph. You'd recognize that because of the form that this function takes on, I have what's called a linear function. Think y equals mx plus b. And playing the role of the m, the slope is 3/4. And playing the role of the b, the y-intercept is -1. So when I'm sketching this graph, I look for my y-axis, this vertical axis, and plot a point where the y-coordinate is -1, corresponding with this -1. And then to find another point on the graph, I take advantage of the fact that the slope is 3/4, and the slope represents the rise divided by the run, maybe is how you were taught it. So from this point, I go up 3 units, 1, 2, 3, and then I go right 4 units, 1, 2, 3, 4, and that gives me another point on my graph. And again, because of the form that this expression takes on, I know that my graph is a straight line. So once I have 2 dots, I'm kind of done. I just need to connect those dots with a straight line, and I come up with my graph. Anyways, if I already had this graph and I was asked to evaluate f of 4, it would be really easy. All I would have to do is recognize that this 4 represents the input to the function, the x-coordinate, and we plot our x-coordinates on the x-axis here. So I go over to the x-axis and I look for the number 4, and I ask myself the question, what is the height of this graph at this point? Well, it looks like the height of the graph when x equals 4 is equal to 2. Therefore, f of 4 is equal to 2, the same answer that I got up here. I said I wasn't going to do any review, and then I did some really basic review. Hopefully that was all really easy for you. Anyways, that's pre-calculus stuff. That's not what I'm supposed to be talking about here today. What I want to talk about here today is calculus stuff. For calculus, we don't care about the height of this graph when x is equal to 4. We don't care that when you put 4 into this machine, 2 comes out. That the height of this line when x equals 4 is this 2. None of that is relevant at all. What we care about in calculus is the rate of change of the function. So not the height of the function, not the output itself, but how much the output changes by when the input is changing. The derivative of the function is what we're going to be studying in this entire class, and all the derivative is the rate of change of the function. We'll learn lots of notation for how to write that, but the most basic way to write it is like this. You'd be asked to evaluate, and it kind of looks like what you're asked to evaluate up here, except there's this extra little apostrophe, right? Instead of evaluating f of 4, what we're being asked here is to evaluate f prime of 4. The way you say this little apostrophe in math is prime, and what this little prime denotes is the derivative. How do you evaluate f prime of 4? Well, what you have to figure out is, at this point where x equals 4, this little red dot right here, at what rate is your function changing? It turns out that's a really deep question that's going to be super hard to do generally in our class, but in this specific example, it's pretty easy. And the reason it's pretty easy is because I started you out with what's called a linear function, and a nice property of linear functions is their rate of change is constant. The steepness of this curve at this point where x equals 4 right here is the exact same as the steepness of this curve at this point up here where x is equal to 7. And it's the exact same as the steepness of this curve at this point down here where x is equal to -1. The defining characteristic of a linear function is its rate of change is constant. So really what I'm being asked, f prime of 4, is the rate of change at this specific point right here. But in this specific example, it didn't even matter that it was f prime of 4. If somebody else asked what's f prime of 8, it's the exact same question because the rate of change is constant, meaning it's the exact same for any value of x on this graph. What is that rate of change? It's something you're already familiar with. It's just the slope. If you're lucky enough to have a linear function, the rate of change, aka the derivative, is just the slope. Super easy. What's the slope of this line? Well, we're lucky enough to have the equation, so we can just look right at the equation and tell that the slope is 3/4. If we didn't have the equation, we just had the graph, we could take any 2 points on our graph. I have these 2 red dots already signified, and just see how much the graph goes up, 1, 2, 3, divided by how much it goes to the right, 1, 2, 3, 4, to get from one of the points to the other point. For this specific function, f of x equals 3/4 x minus 1, if I'm asked to evaluate f prime of 4, really what I'm being asked is at what rate is the function changing at this specific instant right here where x is equal to 4, which is kind of a complicated question. However, fortunately for me, this function is linear, and when I have a linear function, the rate of change is always the exact same. It's just the slope of the graph, which I already knew from, I don't know, pre-calculus, algebra, some point, is just 3/4. So evaluate f prime of 4. F prime of 4 is equal to 3/4. I'm done. A couple quick comparisons for you. We looked at f of x equals 3/4 x minus 1. What if instead we were looking at the graph g of x equals 2x minus 3? Well, again, you might notice that it's in the form y equals mx plus b, playing the role of the m as the 2, playing the role of the b as the -3. So I can come up with its graph. The y-intercept is -3, that's this point right here. And if I think about this 2 as a fraction, it's 2 divided by 1. So I want to go up 2 units each time I go right 1 unit to get another point on the graph. I connect those dots with a straight line, and I've got my graph. What did I call it? G of x, I guess. Here is g of x equals 2x minus 3. I could be asked questions like evaluate g of 4, for example, in which case I'd be looking for the height of this graph when x equals 4, but that's a question that would only be asked in a pre-calculus class. This ain't a pre-calculus class. This is a calculus class. Type of question I might be asked in a calculus class would be to evaluate something like, oh, I don't know, g prime of 1. What is g prime of 1 asking? It's asking me, what is the rate of change of this function g at the point where x is equal to 1. Here's the point where x is equal to 1. How quickly is the graph changing at this point? Well, again, I got a linear function, so the rate at which it's changing at this point is the exact same at the rate at which it's changing at this point or any other point on this graph. That rate of change is just the slope. We already saw that the slope is equal to 2. G prime of 1 is just equal to 2. Might seem like overkill, but I want to look at one more linear function. H of x equals negative x plus 2. The y-intercept is 2, so I'm going to put a dot right up here. The slope is the implied negative 1 that's out in front of my variable here. Negative 1 is a fraction, is negative 1 divided by 1. So I'm going to go down 1 unit each time I go right 1 unit. That gives me a second point on my line. I connect those points with a straight line, and I get the graph of this function, h of x, whose equation is negative x plus 2. Again, I'm not interested in things like h of 3. I'm instead interested in things like h prime of 3. H prime of 3 is asking me the question, at what rate is this function changing when the x value is equal to 3? Here's where the x value is equal to 3. At what rate is the function changing here? At the exact same rate it's changing here, or any other point on my graph. The rate of change is the slope, which is negative 1. Compare these three different answers that I came up with here, these different rates of change. 2 of them are positive numbers, 1 of them is a negative number. Oh yeah, that kind of makes sense if you look at the graphs. For f of x, at this point 4 right here, the rate of change is positive. In other words, as I look at this thing from left to right, the graph is going up. If I'm hiking and this is a mountain and I'm hiking from left to right, I'm walking uphill, not downhill. Similarly, for the graph in pink, g of x, at this point 1 right here, my slope is 2. I'm again hiking uphill as I go from left to right. Note that if you compare these two values, 2 is bigger than 3/4. That makes sense. The pink graph has a steeper slope than the blue graph here. If I'm a mountain climber, I'm walking up a lot steeper slope here than I am over here. The rate of change of the graph in pink is larger than the rate of change of the graph in blue. And then you can compare those to the graph in brown, h of x. When the x value is negative 3, I figured out that the rate of change is negative 1. So at this dot right here, my rate of change is negative. Does that make sense? Yeah, it makes sense. If I'm hiking from left to right, I'm walking downhill. This graph is decreasing as I read it left to right, whereas these two graphs are increasing as I read them left to right. If this feels a little bit too good to be true, if this feels a little bit too easy for a calculus class, well, I kind of got some bad news for you. This is too good to be true. The derivative is really simple as long as we're talking about linear functions, because again, linear functions have a constant rate of change. That's what makes their graphs show up as straight lines. Things get significantly more complicated when my function is non-linear. In our next example, we'll deal with exactly that, a non-linear function and its rate of change. But I want to save that for the next video, because this video, I really just wanted to give you an introduction to what we're going to be talking about and make the connection between this new vocabulary word, the derivative, which I can't overemphasize how important it's going to be in this class, and a concept that hopefully you're already familiar with. This concept of slope. If you're lucky enough to be asked for the derivative of a linear function, really you're just being asked to find the slope of that line, which is something that hopefully you learned in a previous class.